Greetings! This lab will serve as an introduction to a free piece of software specifically written for physics labs called Tracker. It's motion analysis software. It's actually pretty sophisticated considering the fact that it's free. I don't think this existed 10 or 15 years ago. It did, but you had to pay for it. Now, it's free, which is good for you because that means that you can download it and use it on your computer, laptop, or desktop. Okay, first we need to talk about the theory before we look at the applications within the software. So, here's a ball rolling along a surface. It might be speeding up, it might not be. Don't take the length of the velocity vector here literally because it's not going to change during this discussion. So v may be changing. But suppose that you have some means of measuring that speed many times per second. So you're sampling the speed at a particular rate, a particular number of measurements per second. And eventually we're going to plot those speeds versus time. Now we know from our constant acceleration kinematics, the theory behind all this, that the speed at any time should be the initial speed plus the acceleration times how much time has passed since this initial speed. And I guess I'm restricting myself here to a particular type of acceleration because remember, you can only use this formula if what is true about the acceleration? It must be a constant. Now that constant could be zero, meaning it's not accelerating. That's a special acceleration, or a special constant, but any constant acceleration allows you to use this formula. Oh, okay, well this is confusing. I guess I'm specifying no acceleration here. That doesn't work. Let me get rid of that. Okay, well if you look at the form of that equation, v naught plus a delta t, it looks an awful lot like the familiar equation for a line that you learned about possibly back in junior high. In the equation of the line, the way it's typically written in high school algebra courses, you've got one variable, which you might call the dependent variable, which is proportional to, I'm sorry, I shouldn't say proportional to because of the presence of this intercept. It's some number times x to the first power plus a constant. See how the highest power of x that appears in this equation is x to the first power. That's called a linear equation for obvious reasons. It graphs as a line. We call this the slope, and this is the y-intercept. This is the place where the line crosses the y-axis. And that equation has the same form as this equation if we make a couple identifications here. Instead of our independent variable being called x, what if we call it delta t, or time? And instead of calling this number in front of x, m, evidently, we're calling it a, and instead of the constant being called b, our constant is called v naught, and instead of the dependent variable, as you might call it, being labeled y, now we're labeling it v. Otherwise, it's the same dependence, right? There's no x squareds here. By the same token, there's no t squareds up here. There's no x cubed, etc. It's not like we have the sine of x in here or the tangent of y. This is a linear equation. Remember, delta t is really time interval. It's final time minus initial time. Now, if we agree to start our clock at a time called 0 seconds, then t naught is just the number 0, and that means we can get rid of it. And then this really looks like the equation down here. It makes it easy to identify the various corresponding quantities. In fact, that was a little subtle. Did you see what I did there? I switched the order, so I put AT first, because usually we say y equals mx plus b, not b plus mx. That's actually kind of hard to say. B plus mx. It's easier to say mx plus b. So again, the order doesn't really matter. You can add two quantities in either order. Of course, you get the same sum. But when you write it like this, it makes it really easy to recognize that v, in our kinematic equation here, velocity plays the role of the y-coordinate in the familiar equation of a line. T plays the familiar role of the x-coordinate. The number in front of t, which is this constant a, plays the role of m. And you know that m is the slope. So perhaps acceleration would be the slope in a graph not of y versus x, but a graph of v versus t. Now, if we really wanted, we could also use the intercept in the graph to get the initial speed. So here's our fictional plot of velocity versus time. And this is why I couldn't stipulate that the acceleration was 0 because I'm looking at this graph here. This line does not have a slope of 0. What is the slope of v versus t? Remember from calculus, the slope is the derivative. And we know that the velocity, or the derivative of velocity versus time is acceleration. This is something you should know from the previous chapter. The slope of v versus t is the acceleration. So if we were to make a bunch of measurements of speed versus time, maybe you have a radar gun, like a speedometer, well, two different things, but if you have a radar gun that's measuring speed of something and it's hooked up to a computer and recording the data coming out of it, maybe you could actually sample that speed many times per second, take the data, throw it into an Excel spreadsheet, for instance, and make a graph. So a moment ago I mentioned that the letter B here represents the y-intercept. I don't mean for this to be an algebra review here, but that's easy to see because for this point right here, what is the x-coordinate? If you drop straight down, that point has an x-coordinate of 0. Well, if you plug in 0, you would get y equals b. In other words, the y-coordinate of the point where the line crosses the y-axis, that y-coordinate is b. So you can just read it off the graph here, and that'll tell you what number to plug in for b. Okay, let's look at a more restricted situation where, before I move on though, I do want to emphasize what's the whole point of this. If you have a bunch of data for the velocity of something versus time, and you construct a plot out of that data. Now I've got a solid line here, but imagine a bunch of dots on the line representing data points. So you plotted all the data points, and then you drew a line through the data points as best you can. In other words, the best fit line. You could then measure the slope of that line. What would that slope tell you? It would tell you the acceleration of the object in question. Okay, so you're using a graphical tool to determine an object's acceleration. In order to produce that graph, you first need a bunch of data. You need velocity versus time at a number of different times. Okay, what about the specific case of zero acceleration? Well, we know that zero acceleration means no change in velocity, hence no change in speed. So if we imagine taking snapshots of this rolling ball at equal time intervals, like every 1/10 of a second, then the ball is going to move the same distance in each time interval because the speed doesn't change. So that you can read this right off the dots, that the speed is constant. This is something talked about in the very first chapter of your book with those motion diagrams. Now, we do have a kinematic equation that describes the position as a function of time for a constant acceleration. I call that the 1/2 at squared equation. But if your acceleration is 0, 1/2 at squared is 0, and your equation for position becomes even simpler, it turns into this equation. Now this doesn't look too familiar, but you have seen it before. Take this x naught, put it on the other side. Wouldn't that be x minus x naught? What is x minus x naught? That's displacement. So this equation really says displacement equals velocity times time. Now, if the velocity is not changing, then your velocity is the same as it was initially, which means v equals v naught. So this really says delta x equals v naught t, and then I've left off the 1/2 at squared term because the acceleration is 0. This really just says distance equals velocity times time. Right? That's the relationship between the coordinate of the ball at any time versus the time. And evidently, we can also reconcile that with the equation of a line. If you were to plot position versus time for something moving specifically with constant speed, this is only true if the speed is constant. If it wasn't constant, you would have that 1/2 at squared term, assuming the acceleration. Did I say velocity was constant or acceleration was constant? Assuming your speed is constant. If your speed is not constant, that means you are accelerating. If the acceleration is constant, you would have a second term, 1/2 at squared. That t squared is going to screw up your equation of a line. It would no longer be the equation of a line. But for constant velocity, the equation takes on a linear form. So the previous graph, let me go back here, was speed versus time, or velocity. Yeah, I should really say velocity versus time. Now we're talking about position versus time. So if I plot position versus time, go ahead and match this equation up with the familiar equation of a line, and you can see that, again, time is playing the role that x played previously. See, don't be confused by this. Now we're using x to represent an actual coordinate on the horizontal axis. It's the ball's coordinate. In high school algebra, very often when you're doing math problems, you're not actually talking about anything physical, which is a shame because that would make it easier to learn. But x is just some abstract variable. So the role of x has been subsumed by this quantity time, and the role of y has been taken over by this quantity x, the position coordinate. But the form of the equation is the same. Oops, let me back up here. So I don't have boxes this time, but x has now become t, y has become x. So instead of plotting y versus x, we will plot x versus t. Formerly, we called the slope m. Now you can see the slope is the velocity, right? So if you could somehow, maybe you had a camera with the strobe light attached. Or forget the strobe light. Maybe the camera just takes 10 pictures per second. If you went back and analyzed all those pictures, you could determine where the ball was at each moment in time, at each of those sampled times. You could construct a plot of position versus time. You would expect those dots to fall on a line or close to a line because of the equation here. And how could you determine the speed from that data? Just take the slope, calculate the slope of that line. Now, most of you could probably do this with graph paper, right? You know how to plot some points, draw a line through them, and then calculate the slope by taking rise over run for two representative points. So you could do that. We're going to be lazy in some sense and make a computer do that for us. The computer will do a better job anyway. Okay, now what's the other way of saying that the slope of this line would give you the velocity of your object? Remember from calculus, the slope of a function, the slope of the tangent line to a function gives the derivative of that function. What is the derivative of position with respect to time? Of course, that's the velocity. Okay, so when you actually use Tracker, it's going to be up to you to make these correspondences appropriately. And I'll look at an example. What about the case of something falling straight down? This is the most familiar example of constant acceleration. What is the acceleration of something in free fall? Well, if you can ignore air drag, and let me first set up a coordinate system. I've got my origin here. X-axis points to the right, and I've chosen to put the y-axis pointing downwards. I don't have to do that, but if I point it downwards, then I can actually describe the acceleration as positive. We know that the ball is going to accelerate downwards in free fall, and if you can ignore air drag, that rate of acceleration is positive 9.8. Remember, g stands for positive, 9.8 meters per second. Okay, now I'll just interject here, as I often will. It's not really constant, right? The closer you get to the surface of the Earth, the stronger the gravity is, the greater the rate at which you pick up speed. But it's an imperceptible difference. Technically, if you took this steel ball to the top of a mountain and dropped it, it's going to pick up speed at a rate a little bit less than 9.8. And as it approaches the surface, it'll get closer to that value. But it's difficult to tell the difference. So when you're dropping something over the distance of like a room or even a tall building, it's not an important difference at all. Okay. Since the acceleration is constant, it's 9.8, we can use our constant acceleration kinematic equation for displacement. The displacement has two contributions. There's the familiar v naught delta t, which you've known for a long time, and now there's an additional displacement due to the acceleration. Let's modify this equation slightly. Remember, delta t is final minus initial. Let's make the same choice. Let's agree to start the clock at 0 seconds. So t minus t naught just becomes t. And remember, delta y, that's change in position, final minus initial. So since it's minus initial, I'll put the y naught on the other side right here. And see how I've replaced my delta t's by just t's, and I've replaced the acceleration by positive g because I chose to put the y-axis pointing downwards, the positive y-axis. And let's take a look at this equation. Here we have y depending quadratically on the time. Because on the right side we've got a constant. We also have t to the first power with a coefficient, and we have t to the second power with the coefficient. This is not the equation of a line. What would this look like if we were to plot y versus t? Hopefully you know the answer. If you don't, let's make a correspondence between this and a more familiar equation from high school algebra. Very often you looked at equations of this form. Y is some number times x squared plus some number times x plus c. And many of you recognize that that is the equation that graphs as a parabola. If you take a bunch of values of x, plug them into this equation to get the corresponding value of y, and then plot those points, they will fall on a parabola. So we're talking about a quadratic function. Just like before, we can associate corresponding quantities here. So this is the quadratic term in the function. This is the so-called linear term. It's t to the first power. The coefficient in front of t squared is 1/2 g. The coefficient down here in front of x squared, in high school algebra books, it's often just called a. Here I'm writing it as a capital A because that's the way Tracker chooses to do it. Okay, so this might be one of the most important parts of the lab. You have to understand that if you have measured the position of this falling ball at a number of different times, and we're going to do it with a video, a slow motion video, but if you have a bunch of data for y versus t, then when you plot that data, according to the theory, you would expect those points to fall on a parabola. And so we will be asking the computer, hey computer, first of all, please, Mr. Computer or Miss Computer, please find the best fit parabola, the parabola that passes through our data points as well as possible. Once you have found that parabola, please tell us what the value of this coefficient is. And it's going to be up to us to recognize that that coefficient is 1/2 the free fall acceleration. So we can set 1/2 g equal to whatever coefficient the computer gives us from that best fit parabola, and then the last step is trivial, multiply by 2 to find that the free fall acceleration is just twice the coefficient given to us by the computer. And now I think we can actually move into Tracker and look at an example of how this is done. Yeah, so that would be called a quadratic best fit. So here I am in Tracker. Again, it'll be up to you to download this. Make sure you're getting it from the right site. I think if you just Google physics tracker software, it should be the first link that comes up. And the easiest way to get your video into Tracker, and remember the video is in files on Canvas, but it should also be linked in the assignment description. You can just get it from there. I've got some practice videos in there as well. The video that you will be analyzing for submission is called Falling Ball Short, but there will be 1 or 2 other videos. I think it's called Slow Motion Ball, or no, Uniform Motion Ball, Slow or Fast. You should really get some practice with those first. That's what I would do. But open up the folder. After you've downloaded that file, open up the folder containing the file and then just click and drag to drop it in here. That's the easiest way to get your movie into Tracker. Just click and drag and drop. So I have now done that. This is the Uniform Motion Ball Slow video. You may get an error message, something about frames being dropped. Just ignore that, hit OK. And let's get started here. First, let's watch the video. So there's a play button down here. Now he's got this ball rolling along a track. And we're not actually interested in every frame within this movie, because notice that nothing's happening at the beginning. He's just waiting to push the ball. So we don't want to analyze that. Let's grab this little black triangle here and drag it forwards. You got to hold down the mouse, then drag it forwards until we get to the interesting part. See how the ball has already left his hand? so it should already be in uniform motion, meaning constant velocity. And then there's another little black triangle at the other end, and I'll drag that backwards until before it reaches his hand. So the motion that we're interested in is between these two black triangles. Now, we have to tell the computer it has no sense of scale distance-wise or time-wise. The computer does not know whether this motion takes place over 1 second, 1 minute, 1 century. We have to tell it. And we do that by telling the computer what the frame rate is. So up here, there's this little piece of film icon, because, you know, like 100 years before you were born, they actually would record video on film instead of digitally. And see how it's telling us what the start frame and end frame is? Well, that's what we did indirectly with these, or should I say directly, with these little black triangles. So you don't have to mess with those numbers. You do need to tell it what the frame rate is. Now, every time you upload a video, Tracker's going to make some assumption about what the frame rate is. And in this case, I think it's actually correct. It's just assuming it's close to 30 frames per second. So the computer thinks that every one of the pictures in this video captures a time interval of 1/30th of a second, which is this number down here. I'm not going to correct it this time, but it's going to be up to you to enter the appropriate frame rate for the video Falling Ball Short. That's the video that you will be analyzing. In the video, they will tell you what the frame rate is, and it's up to you to put it in here. Now, you can do it one of two ways. You could, like, watch this. If I enter a frame rate of 0.01, wouldn't that be 100th of a second for every frame? That translates to 100 frames per second. So it will automatically take the reciprocal. Just enter one of the numbers. I'm going to go back to 30 frames per second. I don't know why it's 29.97. Doesn't really matter. This is just for demonstration purposes. Hit OK. Now the computer knows what the scale for time is. It still doesn't know what the scale for distance is. So we go up here to this blue. You've got a couple plus signs there. Pull down the menu. We need a new calibration stick. This is how I usually do it. Calibration stick. Okay. And it's telling you you have to shift click to mark. Okay, so I'm going to hold down shift and see how the arrow turned into a square? Cool. Hold down shift, click on the left end. All right, I released shift. Now I click and hold. Oh, that doesn't work. Oh, that's right. They changed it. Okay, so leave that there and then shift click on the other end. What is Windows doing? It's asking me if I want to turn on sticky keys. Get out of my face, Windows 10. Okay. Beautiful. Now we have this calibration stick between the 2 points. Now, who knows why, but the computer, if you look, it's assuming, or the software, for some reason thinks that this distance is 571.3 meters. What a crazy idea. We need to tell the computer, no, that's actually, I think it's 2.2 meters. Yeah, so I'm just, the default units are SI units, meters. So I'll just enter 2.2 and leave it. I hit enter. It added some decimal places, that's okay. So now the computer knows what the scale of distance is. So if I were just to grab a point here and a point here, it could actually figure out that that's something like 15 centimeters because it knows that this is 2.2 meters. Okay, now that you've done that, it's best to hide it. So if I click on this button, it hides the calibration stick. It's still there. It's just not being shown. You definitely want to hide it so you don't accidentally click on it later. Okay, now comes the fun part. We want to track the motion of this ball. So if I hit this button down here, that will take me back to my first chosen slide. And you need to create a so-called point mass. So you go up here, click on create, select point mass, and I think we can change the name if we want. And I'm going to call this the magic rolling ball. You can call it whatever you want. You don't really have to call it anything. And, wow, it's been a while. If I hold down shift, oops. Okay, check this out. When I hold down the shift button, again, the arrow turns into a box. While you're holding down the shift button, and you probably want to, whoa, what's happening there? I want to to zoom in. Why is it not letting me zoom? Usually I put the two fingers on the mouse pad and do that thing. Okay, let me pause and figure out how to zoom. They seem to have changed it here. Yeah, it must be this button up here. Let's zoom into 200%. Cool. And now, see, now I'm trying to, I guess I have to use the menu bars. Normally you can just use the mouse to do this sort of thing. I think I've zoomed in too much. 1200%. I don't know how that happened. Okay. So, hold down Shift, click on the center of the ball. And now you'll notice this little dot appears on a graph of x versus t. So the software has recorded the position of the ball for that frame. Do you notice now the little marker is not at the center of the ball? That's because the software has automatically advanced to the next frame. So it's time to repeat what we just did. Hold down Shift, click on the center of the ball again, and I'm just going to keep doing that. It's a little tedious, but what I'm doing is tracking the motion of the ball in time. And you'll probably want to zoom in and try to do this more precisely, like try to click on the exact center of the ball each time. Sorry, these sticky keys keep popping up because of Windows 10. Okay, this is kind of annoying, is it not? Because we've got a ways to go. I mean, how many times do we have to do this? But that's enough data already, I think, to show you what the whole purpose here is. Ideally, you would continue doing that until you had finished with all the usable frames. Okay, over here is the plot window. Now, you see how there's a boundary between the video window, the plot window, and this data table? You can adjust those boundaries. If I put the mouse right here, see that? I click and I can drag to make the plot window bigger if I'd like to do that. I think if I click on this, what happens? Choose a view. Plot view. I see. You can make some choices here. I'm not going to worry about that yet. But do you notice how x versus t already looks the way we expect it to look? It's got a roughly constant slope. So I am going to right-click and scroll down to Analyze here. Analyze. And it automatically pops up this plot, and I really hope this is showing in the video here, in the video instructions. Yeah, maybe I should stop this video and check, because if you can't see this, then there's no point in doing this. Okay, the plot window, which they're calling data tool up here, it does come up in a separate window. That's why in Zoom I had to pause and reopen, but here we are in the data tool, and there's a number of things we can do here. And we've only got two variables to work with, x versus t. I just remember that menu that I pulled up and I scrolled down to Analyze. Well, let's hit this button to Analyze again. So you do Analyze twice, once in the menu and once here. And I would like to do a curve fit. And when we say curve, it doesn't have to be something that's actually curvy. It could be a specific curve called a line. And that's actually the curve that I'm interested in at this point, because I expect position versus time to be a graph, or I expect those two variables to graph as a line. So the first thing you might want to do is to check down here in the lower left. There's a box that says Autofit. You want that to be checked. That means that the software has attempted to draw a best fit curve through your points. Now, what type of curve? That's what you choose right here in this menu. You probably haven't learned about Gaussian curves. You do know about exponentials. You know about cubic functions, parabolas. Well, we want specifically a line. That's the default best fit anyway. And there's the form of the equation that we talked about in the slideshow, or in the PowerPoint slides. Although they're not saying y equals a x plus b, they're actually using the variables, x and t. But here's our linear fit. Notice that this is the equation of a line, x equals at plus b, and from the theory we talked about in the slides, we know that that coefficient, capital A, should be the slope, which we can identify as the speed. So we would just like to extract the value of A from the software, and they're giving it to us right here. 3.25 E negative 1. What's up with this E negative 1? That's an alternative notation for times 10 to the negative 1, right? Times 10 to the negative 1. Well, 10 to the negative 1, that means dividing by 10, does it not? Times 10 to the negative 1 is divided by 10 to the first power. So you would take the decimal point, move it 1 to the left, and evidently A is 0.325, 0.325 meters per second. Remember, tracker's going to deal with SI units, 0.325 meters per second. You could multiply it by 100 if you'd like and convert that into 32.5 centimeters per second. But this is what you will be doing in your lab. The necessary parameters that you need are listed right here, and it's up to you to interpret things correctly. Now, suppose some of this data was considered bad data, like, I don't know, if we could tell that there was a kink in the graph here when the ball hit a little bump on the track, and so we only wanted the velocity before the bump, what we can do is just highlight the good data. So click and drag see this green rectangle? Drag that rectangle around the data that you consider to be good data, and the software will ignore all of the points outside the rectangle and only focus on drawing a best fit line through the highlighted points. Keep that in mind later in the semester when we use the software to do something a little more interesting than what we're doing here. The purpose of this lab is to get you familiarized with Tracker and also to measure directly the free fall acceleration. Okay, is there anything else I can say about this? Sometimes you may end up with multiple columns here, and you don't necessarily want to see all those columns, so what you can do is right-click on the column heading and cut the column. And in this case, it seemed to have gotten rid of all the data. So let's go back and look at something else that we can do here. Now that I'm back in the main menu here, or the main window, there is a feature I should point out. If you don't like how small the type is here, especially if you're showing this on like a projector, you can make it bigger with this button here. Just tap that a couple times to increase the font size. That's a little too large, and now how do I get back to where I was? Because, here we go. Okay, now, in this window, the plot window, before I go to the menu, remember you right-click, go down to Analyze. Before you do that, you can actually decide which quantities are plotted on the graph. So if I click right here, look at all those options I've got. Instead of just plotting x-coordinate, I could plot the y-coordinate. I could plot the distance from the origin. It will even calculate velocities for you. That's important for this lab. In the written lab instructions, which are posted in the assignments page on Canvas, you will be instructed to plot velocity versus time in addition to position versus time. And this is where you would go to choose which quantities are on your plots. You know, what's the y-coordinate, so to speak, and what's the x-coordinate. Don't be confused by that use of the letter x. The generic sense of y and x is just vertical coordinate and x-coordinate, or a horizontal coordinate, excuse me. Okay, now the video that you're using has way more frames in it than the frames that I just dealt with, and you're probably not going to want to do that plotting procedure, or excuse me, the tracking procedure for that many points. So here's another way to do it. If you hover over one of these points and you'd like to get rid of them, hit right-click, go down and select Clear Steps. So all that data is gone. And I'm going to start over. So I go back down here, I back up to the initial frame, and I would like to zoom in here, and last time zooming in gave me trouble. That's pretty good. So let me get the ball centered in the screen. And notice I still have my my point mass here. If that for some reason goes away, you have to get it back. You might want to just close out the program and start over, or go back up and create another point mass. But now let's look at how to use the Auto Tracker feature. That's this button right here. So if I click on that, the Auto Tracker window comes up, And you want to check that currently you're tracking your ball, whatever label you gave to it. You want to see that here, because sometimes it gets messed up and it's trying to track something else. We don't want that. So make sure that you're tracking the object you're interested in. And now, see, it's giving you some instructions down here. Shift click. Is it shift? Wait a minute. Okay. Yeah, it's not just shift click. It's shift control. To do it manually, you do shift. So right now, if I just hold down shift, my mouse turns into a square. And you know what? I just realized you can't see the auto tracker window because of the way Zoom works. So hang on just a second, and I'll pull that auto tracker window up. And unfortunately, I don't think I even see it. Okay, well, I hope you can see this window. Okay, so if I hold down shift, you get the square. If I hold down control shift together, it's a circle. That's what we want. So click on that circle. Beautiful. And now we get what I believe is called a key and a template. No, search window and a template. That's what it is. Let me zoom out a little bit here. Here's how this works. The computer or the software is going to memorize all of the pixels inside this circle. And then on the next frame, it's going to look for that same group of pixels, but it's not going to search the entire screen. That would take the computer too long. So it will only look within this square for that group of pixels. And we're free to adjust both the template of pixels and the search window. There's no need to search up here for those pixels in the next frame because the ball's not going to be up there and it's not going to be down here. It's only going to be somewhere on this track in the forward direction. So I'm going to hover over the corner here. You get the hand. And let's adjust the shape and size of the search window. The computer only needs to look in the forward direction within this narrow interval here for those pixels. And I probably could get away with doing this even because I don't expect the ball to move very fast. But just in case, I'll give it a little bit of room in the forward direction. And also, I don't need to grab that many pixels. So when you do this with the falling ball video, you want to make a smart choice of pixels to grab. If you think about it, as this ball moves down the track, won't the background up here change? Like when the ball gets here, this background looks a little different than it does here. And that's going to confuse the software. If I only grab pixels belonging to, let's say, the bottom half of the ball and the track, that should stay pretty consistent throughout the ball's motion because the colors of the track don't really change and the ball itself doesn't change. So this is a fairly smart choice for auto tracking. I think the computer should be able to track these pixels from one frame to the next. Okay, now I have to hit the search button on the auto tracker window, and I really hope you can see this in Zoom. I think you can. So here I go. Let me zoom out first so we can see what's happening in the forward direction. Okay, once you're ready and you've got your template chosen and all that, I'll hit search. There it goes. So I got lucky this first time. What would happen if you made a poor choice of pixel choice, or a poor choice of template, shape and size, and search window, is the computer would get stuck on one of your frames. That's probably more data even than I need. Okay, so now it's finished. It's gone through all the chosen frames. It didn't have any trouble throughout that motion, which is great. Now, if you get hung up, if the computer gets hung up and you want to start over, just like before, I think you would right-click and delete. You could even go down here, if you can see the auto tracker window here, and hit delete. There's a pretty intuitive way of clearing your steps and starting over. That's what I would do if it gets hung up. Just start over. Okay, so now I've got a significant amount of data that I can work with. Let me close out of the auto tracker window here. And what just happened to all my data? I don't even see it. What happened to my data? If I go to analyze, okay, so it's there. Let me pull that up. there is all my data in the data tool window. Okay, so just like before, this time, interesting, see how it did not automatically check the Autofit button. So it's up to me to click Autofit. Now, you probably can't see it, but it drew a line through these points, and it's a purple line usually. I can just highlight those points and ask for that best fit. You may notice there's a very slight amount of curvature here, and that's because the ball is gradually slowing down due to friction. You can see the slope here is just a little bit less in magnitude than the slope here. In any case, I do want my linear fit. I could use the parameter here, A, to get the velocity, because we know the slope of position is velocity. Now, when you do the falling ball, you're going to determine G using two different methods. Once will be a linear fit of velocity versus time. So when you do the linear fit, these variables need to be velocity versus time. And you can't change that here in the data tool window. You would have to do that in the previous window. Remember I showed how you can click on these quantities and choose what you want to plot? You can't do that in the data tool window. But when you plot velocity versus time, make sure you select velocity as your vertical coordinate, and then you would be doing a linear fit. If you had plotted the y-coordinate versus time, we've already talked about this in the PowerPoint slides, you would expect a quadratic function. So that's where you would go here and change your best fit to a parabola. Now, of course, that doesn't apply to this rolling ball here, but make sure you choose the correct type of curve to do the fitting. And I think that's probably all you need to know here. Yes, as far as exporting your plots as images, I think there's, what is it, a snapshot or snapshot tool with Windows now, where you can take a picture of the window that you have open. You can also just do print screen. That might be the easiest thing, because here's something you must include in your report, and this is in the written instructions as well. I want to see this plot, but I also want to see the best fit equation down here, including the parameters. And you have to indicate in this window how you determined G. So that may involve circling something and writing a little calculation off to the side, but I need to see how you determined G. Now you may decide you want to type that out separately, that's great, but I also would like you to indicate that on the plot here. So if you print screen, you can just copy the whole thing, paste the whole thing into a Word document, do it that way. There's also this option, what is it? File, export data. I know there's a way to actually export the picture itself. What if I right click here? Snapshot, aha. See, if I right click and snapshot, you probably don't see it, but it's opening up in a separate window. Yeah, and I can file, save as a JPEG. Okay, so again, Zoom, I don't think Zoom is showing this to you, but one thing you can do is right click, snapshot, and right now I'm seeing a separate window. I can go to File in that new window and save as a JPEG, or you can even print. The problem with that option is it won't include all this data down here, and I do need that data, so you should probably just print screen. Now, there's no need to do this, but I can also export this data into Excel. So what I'm going to do is go up here to File, Export Data, and I don't have any, it doesn't give me any options about which data to export, so I guess we'll find out. I'm saving this to my desktop here. Let me pause. Yeah, that didn't work out so well. It looks like you had to export as a text file. If anything, you'd want to export as like a comma delimited or tab delimited file. But check this out. Here's an easier way to do it. I can just click and drag. Let me get this column too. Whoops. Click and drag over all the data I want, and I'm going to do Control Copy. So I copy all that data. Now I'm going to pause for a moment and open up Excel here. Okay, awesome. So that worked. All I did was open up a spreadsheet and do Control V to paste the highlighted data into Excel. And now, if I'd like, I can actually plot here in Excel instead of Tracker, because if you like to tweak your graph, there's more things you can control here in Excel. So again, I'll go to Insert. I want to do a scatter chart. I'm glad it didn't make any assumptions about which data I should be be plotting. So let me go to plus. No, that doesn't work. Right click in the middle here, select data. Okay. And I want to add a data series. Again, you don't have to do it this way. You're welcome to just take the plot, screenshot the plot out of Tracker along with those parameters and then paste that into a Word document. But my series name would be X versus T in this case. Now they're calling it series X values. They really mean the horizontal coordinate, but I would like to plot the time on the horizontal axis. So I will click and drag over all these T values. Then down here I have to delete this junk that they put in there. And I click and drag over all my X coordinates. Now they're calling it actually the Y values. I know that they really just mean vertical coordinates. I would like my vertical coordinate to be the X coordinate. So I find it's useful to hit Tab in order to actually enter that into Excel. Then you hit OK, hit OK again. That's a nice graph. Definitely a linear dependence there. And now I can right click on the data point and add a trend line. You can do it that way, or you can do it up here. Add a trend line. Did it do it? It's kind of awkward. So let me do it the first way. Format trend line. There we go. If I would like to format the trend line, that gives me the option to display the equation on the chart. Great. And then of course you can scoot this over. You can click in there. Once you've clicked in there, if you do Control A, it'll select everything. And then I can increase the font size a few times. That's nice. I can actually change the variables to their appropriate names, which is X coordinate, depends on time. And there it is. There is the slope, which we know to be the velocity. That would be in meters per second. So you could circle that, hand circle it with the pen, and I would need you to identify that as the velocity and write that on your plot. So somehow you need to indicate to me how you got, in your case you're not doing velocity, you're doing free fall acceleration, how you got g from the equation of either your line or your parabola. And you're using the kinematic equations to guide you for whether you are supposed to be doing a linear fit or a quadratic fit. Right? That ought to be enough to do this lab. Just a couple final points about Tracker here. Summarize. When you first open it up, remember you have to go to the clip settings. Make sure you enter the appropriate frame rate. Make sure you go up here to this icon, and you have to create a calibration stick as I demonstrated. After you've made the stick, see how you can see it here? Tap that button again to hide it. Now, something you do want to do this. I left this out, and this is very significant for your lab. You need to choose a coordinate system. See how there's a button here for axes? Okay, so we've got an X and Y axis here. If you hover over the center, it turns into a hand. You can click and drag. It doesn't really matter where you put the origin, but you want to make sure that one of your axes, in this case my x-axis, I want to make sure that the x-axis lines up with the track. So if I move over here, it turns into a hand again. I click, and now I can tilt this back and forth and make sure that it lines up with the track. My data came out okay because it already lined up pretty well. When you do your lab, your video will be a falling ball next to a meter stick. So it's up to you to make sure that the y-axis here lines up really well with the meter stick. Because if it doesn't, you're not actually finding the y component, you're finding the component along some other axis. Yeah, so that's another point. If you have this vertical axis aligned with the meter stick, then what you really want to plot is the y coordinate versus time, or the y velocity, depending on what part of the lab you're doing. Another way to do it would be you could just tilt the x-axis down so that it lines up with the meter stick. If you do that, then you really should be plotting x versus t or x velocity. So if you get really weird data, it could be that you didn't actually line your axis up with the meter stick, or that you're looking at the wrong axis. Once you you've got your axes set up, you should hide them again. Get rid of them so that you don't accidentally auto-track those instead of the point mass itself. Okay, so there's that point. And what else did I want to tell you about this? Yeah, if you hit a snag and you really can't figure out what's going on with your data, one thing you could do is just close out the program and reopen it, because it's not a perfect piece of software, and I have noticed an occasional bug. All right, that should be it. Don't forget to choose the appropriate frames down here. You don't want to watch the entire video necessarily. And there's one other thing. Right, in the falling ball video, that meter stick is hard to read. The text is really grainy. So what you'll have to do when you create your calibration stick, how do I change this one? Yeah, once you've created your stick, put the top of the stick on some number that's actually legible on the meter stick. And then you'll put the bottom of the calibration stick at another number that's actually legible. So let's say this top was at 30 centimeters, because you could actually read that number, and this was at 10 centimeters. You would need to take the difference between those two coordinates and enter that in here. Does that make sense? Why am I asking you that? You're not here to answer that question. But we know it's a meter stick, but you can't see the entire meter stick in the video. So pick two numbers that are actually legible on the meter stick, figure out the distance between those 2 points, and enter that appropriate distance in here so that the computer knows what the scale for distance is.